we are going to talk about nucleophilic substitution. So what is a nucleophile? Well, nucleo is nucleus, phile is loving, so nucleophiles really want to be near nucleus. Nucleus has got positive charge in it, right? So then what kind of charge does a nucleophile have? Negative, or partial negative. So this is our nucleophile, and we're often going to draw it with a lone pair of electrons because these electrons are going to be doing some reacting. And if we have our electrophile, which is the thing that wants these electrons, over here, this is going to be something that has a positive, or usually partial positive in organic chemistry, partial positive charge. And this nucleophile is going to attack the electrophile with its electrons. So usually that means forming a bond with the electrophile using those two electrons. And this arrow is how we draw reaction mechanisms. So we always draw the arrow from the electrons to the electrophile. So nucleophiles can vary in their strength. The stronger nucleophiles are going to be the ones that want to react more. And there's three kind of things that we consider here. So the first one is charge. And so if you're negatively charged, this nucleophilicity goes up. The second thing we consider, and I mean the second and third things are kind of both under the same umbrella, so this is going to be, the second and third is electronegativity. And actually, it's kind of weird because we want electronegativity to be down. And the reason why that is if your electronegativity is too high, you're going to hold on to your electrons too much and you're not going to want to share them with an electrophile, right? If we draw out a periodic table, all these guys in the S and D block, they're going to form positive ions, right? So we don't want them to be a nucleophile because a nucleophile has to be negative or partially negative. Over here, what's happening is the electronegativity is going up in this direction. So I'm going to call this electronegativity. So, by that logic, nucleophilicity goes up in the other direction. And so the two kind of parts of this that I was talking about is that nucleophilicity increases down the table, and nucleophilicity increases toward the left of the table. So if we look at some nucleophiles, this is a nice little table showing the strength of nucleophiles. If you're on a device that screenshots, maybe screenshot this one. But you can see all the really negative stuff is over here in the strong nucleophiles. And then if we go over to the weak ones, they're going to be the ones without a charge. And then if you want to look at electronegativity, we can take the case of the halogens, right? So if we look at the periodic table, it goes fluorines on the top, then chlorine, then bromine, then iodine, right? So nucleophilicity is going to go up this way. And we can see that we have fluorine, chlorine, bromine, and iodine in that order. And so even though all of these are represented here as negative ions, fluorine still falls into weak, and chlorine is still not that great either because they're so electronegative that they hold on to their electrons so much that they do not want to give them away or share them in a bond. They're too selfish. So that's what a nucleophile is. Now let's look at the substitution part of this. So there's going to be two types of nucleophilic substitution, and they are called SN1 and SN2. S stands for substitution, N stands for nucleophile, and the 1 and 2 refer to the order of the reaction rate. So rate equation shows us that rate is going to be equal to K, which is a constant, times the concentration of whatever reactants to some power, right? And the total powers of all the stuff is the order of the reaction. So if I have like just this one reactant that I'm calling A, this is a first order reaction. If I put A to the 0th power, it would be 0 order, and this would be crossed out, and K is just the rate always, right? If I make this squared or cubed, it will be second order or third order. But that's not what's going on in SN2. In SN2, when you have second order, it's because you have two reactants that are dictating the rate. So this is for SN2. SN1 is going to have this other one where it's first order, and that's why we call it SN1. So rate is going to be equal to K times just the one reactant, and we are going to see why that is as we get into it. So what's going to be kind of backwards is that SN2 is 1 step and SN1 is 2 steps. So we're going to start with SN2 because it's simpler and it's all compact. So let's say I have an electrophile, and when it's a whole entire molecule that's our electrophile, we like to call it the substrate. And this substrate has to have a partial positive thing, which will be this carbon, and it has to have a leaving group. That's the thing that's going to get out so we can substitute something else in there. And that's going to be the bromine, and it's going to have a partial negative on it. And this partial negative is going to kind of allow it to, when it leaves, it's going to be a complete negative. And whatever charge or partial charge that the nucleophile had, that's going to make the bond and balance out the partial positive with carbon. So if we have a nucleophile, let's use I minus, right? Because iodine is more nucleophilic than bromine. That's something that I need to also explain, is that the leaving group is going to leave based on reverse of nucleophilicity. So basically, if you're a better nucleophile, you want to attack this thing more, then you're worse at leaving, right? That makes sense. Because this is actually always going to be in some kind of equilibrium of iodine trying to kick bromine out and bromine trying to kick iodine out, and iodine's going to do the better job of the kicking out. So iodine is going to take one of its electron pairs, it's got 8 in its negative ion form, and it's going to take that and attack this partial positive carbon, right? Electrons attacking partial positive. But wait, carbon can only have 4 bonds, so what the heck is going to happen now? Well, we're going to get rid of this bromine. So this line that's bonding carbon and bromine, that's actually a pair of electrons, right? That's how we make bonds, as we share electron pairs. So those electrons are going to both go off with bromine. And we're going to get our product, which is CH3I, or iodomethane, right? And we're going to have a Br minus hanging around somewhere here. And those extra electrons are going to be there. So originally bromine had 3 lone pairs, right, and 1 bond, and that was 8. Now bromine has complete octet, no bonding, no sharing, all by itself. So I hope this makes sense. We're going to get into a little fancy thing that happens with this SN2. So let's say that I don't have this CH3I thing. Let's say instead that I had something that was chiral. And if you don't know what chiral means, I would advise you to go and watch my video on stereochemistry and enantiomers, and you'll learn all about it, and then come back. So you've come back, or you never left because you know what chirality is. We're going to draw a chiral carbon, or a carbon that has 4 different things bonded to it. So we're going to have a methyl, we're going to have an ethyl. I don't want to draw that there. I want to draw our ethyl here. This is going to be our leaving group again, which is a bromine. We're going to make it kind of the same. And then back here, we have a hydrogen. Okay, we're going to have the same nucleophile. We're going to use I minus again, because we know it can kick out bromine. What did I just do? We know it can kick out bromine. So this iodine is going to think about where can it attack to kick out bromine, and it's going to end up doing this thing called a backside attack, which is just what it sounds like. It's going to attack from the opposite side of the atom, of the carbon atom that bromine is bonded to. So I'm going to try to make an arrow that is also dashed to symbolize that this is attacking back here, and bromine is going to leave. So what's going to happen with this backside attack is this whole thing is going to flip inside out like an umbrella, and it's going to get to be the other configuration. So let's say it's R, then it's going to turn to S. If it's S, it turns into R. It's going to flip around. So let's do our little priority system here. We've got bromine at number 1 because it's the heaviest. Ethyl is going to rank number 2, then methyl, and finally hydrogen is number 4, which is in the back as it's supposed to be. Okay, so if we go 1 to 2 to 3, we get R, right? Because it's clockwise. So the product that we make out of this is going to end up being S. So what we're going to get is, I want to switch back to the other color. We're going to get our methyl, our iodine, our ethyl, and the hydrogen. So this should be correct. 1, 2, 3, 4. If I'm going too fast, pause the video and think of it yourself so that we are on the same page. Okay, 1 to 2 to 3. That is S. So this is the backside attack. This is called inversion of configuration. So we are basically taking the stereochemistry and we are switching it. So if you get a question about SN2 and they're like, oh, we have R2-bromobutane and we put iodine into it and kick the bromine off, then what's going to happen? It's going to turn to S. So that's SN2. Now we're going to look at SN1. And SN1 is a little bit more complicated because it's got 2 steps. That's why the rate is only going to depend on one of the reactants, because in the first step, only one thing is reacting. Whereas in SN2, we had both the things reacting at the same time, so the concentration of both of them would matter with the rate, right? So now we're going to look at SN1. So for SN1, we are going to start out with this. And it's going to have bromine. We're going to do the same thing with bromine and iodine. And iodine is not going to enter the picture yet. We're going to do this weird thing where bromine is going to leave all by itself. And this is going to create something called a carbocation. So carbo, carbon, cation, positive charge. Because the bromine went off to be negative, right? So we have to have something that balances that out, and that something is this carbocation. When I first learned about carbocations, I wanted to call them carbocation, like a vacation. But even though it's kind of spelled that way, it's a carbocation, like a cation. Anyways, so the next thing that's going to happen is iodine is going to come along with it, all of its electrons, and it's going to take one of its electron pairs and it's going to pop right in there. And this is going to make us our product of tert-butyl iodide. So that's SN1. Hopefully it's not too bad, but we've got some little quirky things that go on with SN1. One of these little quirky things that goes on is called rearrangement. So let's say that instead of a tert-butyl bromide, we started with, I don't know, a cycle, and we have bromine on here. Ooh, we're getting fun and complicated. Okay, so bromine is going to leave, right? And we're going to get a carbocation. And the Br minus that floats off into somewhere. So this carbocation has some stuff happening to it. Remember electronegativity, and remember how we can have a dipole moment. So let's say we have a carbon and a bromine. We've got bromine pulling electrons away from carbon. We call this an inductive effect. Specifically, this is called a -I inductive effect because it's an electronegative thing, pulling electrons away and becoming partially negative. Well, here we have carbons, and carbons are not electronegative. They are what we call electropositive. So they're going to basically do the opposite thing, and they're going to push electrons at other stuff. We call this a +I inductive effect because the carbon is pushing electrons away and getting more positive. So these carbons here and here, they're going to sense that the guy between them is positive, and they're going to go, oh, you're deficient in electrons. We're going to help you out. We're going to give you some of our electron density just to make up for it so that we can all delocalize this positive charge just a little bit. So you're going to get some electron density coming toward this carbon. And that's going to stabilize it. That's why it's better to have more carbons around a carbocation. So this carbon goes, okay, well, I'm stable. I'm a little bit more stable than I was before because my friends are helping me out. But you know what? I could do even better. I could have even more friends. And the carbocation is going to look at its neighboring positions. And if there's one where it can get more help from more carbons, it's going to just kind of hop over there. So I'm going to take away these things. And we are going to zoom in on this part. So we have this carbon that's the carbocation, right? And it's bonded to this carbon. And it's also bonded to this carbon that's bonded to two other ones, right? And this one also has a hydrogen. And this one has a hydrogen. Okay, so what's going to happen here is something called a hydride shift. So this little hydrogen here is going to just pop next door. It's going to take its electron pair with it, and it's going to go to that carbocation. And that carbocation is going to kind of disappear off that one. No more carbocation. We have another hydrogen. We have 4 bonds. We have 8 electrons. We're happy. What about this one? This one only has 6 electrons now, right? So it's positive. Except this one is kind of luckier, right? Because there's 3 carbons around it. And all these 3 carbons are going to be pushing in electron density into this carbon. And it's going to be more stable than the other cation was before. So that's what's happening. And I'm going to erase this. So if you want to take a look, pause the video now. Okay, I'm erasing it. And I'm going to redraw it on the regular mechanism that I had up there. So we have a hydrogen here, right? And we have a hydrogen here. And this one's just going to go on over. And this is going to get us our new carbocation here. And then our iodine can come in with all of its electrons. Take one of these electron pairs that are not drawing for some reason. Okay, now they're drawing. And it's going to attack this positive carbon, and we get our product. So you might be wondering, well, do we have this crazy stereochemistry thing that we had with SN2? Well, the thing is we don't, because in SN1 we are always making a carbocation. A carbocation has 3 bonds and no lone pairs. That's why it's positive. So it can't be chiral ever because it's bonded to only 3 things. And now that there's only 3 things, those 3 things have got plenty of room to move around and shift and change where they are. So by the time that this iodine comes in, even though, actually this carbon isn't chiral, but let's pretend it was. If this nucleophile comes in, some of them are going to be one way and some of them are going to be the other way with the 3 things that are on there. So what's going to happen is something called a racemic mixture, where we have some of the R and some of the S. And that's always going to be the case in SN1. You never end up with a stereoisomer, like all R or all S of this carbon that we made positive. Maybe other carbons on this compound are going to have stereoisomers, but this one is now always going to be a racemic mixture if it's chiral, the one that got attacked. So I kind of started to introduce the concept of inductive effects plus I inductive effects, and how if we have more carbons in an SN1, in a carbocation, we're more stable, right? So we have names that we give these different kinds of carbons. So if we have a carbon and it's bonded to one other carbon, we call this primary. If we have a carbon that's bonded to 2 carbons, so like this one here is secondary. And if we have something that's bonded to 3 different carbons, like that one on the cyclohexane that we were looking at, this one here, we call this tertiary. And there's kind of a secret 0-1, I'm going to kind of squeeze it in here, where if you have, this X might be like a halogen or whatever other nucleophile. If you have only one carbon in the entire compound, we call this methyl. And when you have an SN2, things are going to go, they're going to get better this way. So this is SN2. And the reason why is because the nucleophile is coming in at the same time that the leaving group is leaving. So you don't have a lot of room in there, and the more carbons that you have around it, it creates something called steric hindrance, which is basically you don't have space to get yourself in there. So that's bad for SN2. In SN1, we always have a carbocation, and so we have a little bit more space because there's only 3 things bonded. But the important thing is these plus I inductive effects that are pushing in electron density and stabilizing your carbon. So things are going to get better in SN1 as we get more toward the tertiary carbon. Now in SN1, there's another secret thing that goes here, and that's resonance. So let's look at that for a minute. Sorry, this takes forever to erase. Okay, so let's say that I have this. No, I want to keep using the BR. And this is going to be an SN1. If this bromine leaves, then we have this carbocation here. And this actually has a resonance structure where we can move the electrons and make a new thing. So if we move these 2 electrons and we put the bond in here instead, because we can fit that bond in there, everything works out, then what we get instead is this. And you might look at this and go, oh my god, it's a primary carbocation. This carbocation must be so unhappy. But if those electrons can delocalize between these 2 positions, because what happens isn't that the double bond keeps jumping back and forth. That's not what happens. What happens is what we call a resonance hybrid, which is where basically it's like half one structure and half the other structure, and the electrons are kind of just floating around delocalized between. That's more stable. That's better than even having a tertiary carbon. Resonance beats all with carbocation stability. So you can imagine, for example, if you have a carbocation that's conjugated to a benzene ring, so let's say that this is your carbocation, you've got a whole ton of options for resonance because you've got all these conjugated double bonds, or double bonds that are 1 carbon apart. So these are really good carbocations if you've got a benzene ring. So that's resonance. And we talked a little bit about how primary, secondary, and tertiary affect SN1 and SN2. And I'm going to draw that out again really quick because there's something that I forgot to say. So we have methyl, right? We have primary, secondary, tertiary, and resonance sometimes. Well, in SN1, things get better this way. SN1, things get better this way. And in SN2, things get better that way. But in SN1, it's so bad if you have a methyl or primary, it's so unstable that those things are not going to happen, ever. If you have a methyl or a primary not carbocation, because it's not going to go. If you have a methyl or primary carbon, then SN1 reaction will not go, and if you have a problem and you're deciding, is this SN1, is this SN2, you know it's SN2, because SN1 will not go. Likewise for the SN2, resonance doesn't really play a role, so we don't really care about that, but tertiary carbons are so crowded that SN2s are never going to go with tertiary. So the kind of carbon is one good factor in how to decide if a reaction is SN1 or if the reaction is SN2. There's 2 other factors that are pretty convenient with this. One of them is strength of the nucleophile. So SN2 likes strong nucleophiles. And that's because the nucleophile has to be strong enough to get in there and kick out the other thing. And all this, it's attacking a partial positive. So, meanwhile in SN1, we're okay with weak nucleophiles. And the reason why is because we have a carbocation that's completely positive, so it's going to be better at attracting stuff even if the nucleophile is not too great. The last thing that we want to look at is the solvent. So actually what can happen is if you have a reaction and you're dissolving it in something and you're running an SN1, right, and you get a carbocation, intermolecular forces between the carbocation and the solvent can actually help stabilize the carbocation. So if you have SN1, we like to use what we call aprotic solvents. And aprotic sounds like proton, and that's going to be because aprotic solvents are basically any solvent that hydrogen bonds. And just to do a quick review, hydrogen bonding happens when you have OH, NH, or FH bonded directly to each other. The weird thing, though, about FH is those both can only make one bond, so the only thing that you get is hydrofluoric acid, and I've never seen that used as a solvent, so don't worry about fluorine. Okay, for SN2, then we use what we call aprotic solvents. And there are some common ones you might want to know. One of the really common ones that people use in organic chemistry is called acetone. This is the same stuff you use in like nail polish remover, and it's a really simple ketone. It basically looks like this. So it's 3 carbons and the ketones in the middle. The other one to know is DMSO. DMSO stands for dimethyl sulfoxide. And I feel like there might be one other, but I can't think of it right now. If it turns out there is another that I think is important, I'm going to put it in the description of this video. Okay, so those are the 3 things that you look at when you want to decide SN1 or SN2. And I think this is really, really cool, especially if you're planning on going into something like medicine. This is like making a diagnosis. So basically all you have to do is if 2 of these line up, then it's that one. And if 3 of them line up, you're super lucky. Okay, so that's how to tell SN1 or SN2.